Hey everybody. Um, how's this for volume? Is that a good place? I think that's about where I had it last time. Cool. And then let me change. Hey, deleted user. There we go. You're also building a programming language? Awesome. I'm not going to be doing that in this stream. This stream is for learning assembly for my hypothetical operating system, but I'll give people a minute or two more to get online while I get this set up, and then we'll get started. I feel like my camera's kind of fuzzy. That's better, isn't it? Okay, and then where's our book? So we're here. Can I like unhighlight this? Check it out. I can. I'm gonna go throw on a long sleeve shirt or a hoodie or something. I'm a little bit chilly. I'll be right back. Sometimes it's kind of dead. I can barely keep up with your guys' messages on there. But yeah. Cool, yeah, you should totally get in. Did you see how many people were getting on? Like yesterday? It was crazy. Well, and today, I guess. I think we're getting pretty close to 100. Yeah, Stefan, close to 100. All right, cool. We got enough people to get started. I'm going to start reading through this. So chapter 4 is about virtual memory. This chapter covers virtual memory as implemented in Intel 64. We are going to start by motivating an abstraction over physical memory and then getting a general understanding of how it looks like from a programmer's perspective. Let me make this easier to read. Oh, it's already on. Oh, that's off. Okay, we'll keep that on. Yeah, pretty close to 2,000 subs. Finally, we will dive into implementation details to achieve a more complete understanding. 4.1 Caching. Let's start with a truly omnipresent concept called caching. The internet is a big data storage. You can access any part of it, but the delay after you made a query can be significant. To smoothen your browsing experience, web browsers cache web pages and their elements, images, style sheets, etc. This way, it does not have to download the same data over and over again. In other words, the browser saves the data on the hard drive or in RAM, random access memory, to give much faster access to a local copy. However, downloading the whole internet is not an option because the storage on your computer is very limited. A hard drive is much bigger than RAM, but also a great deal slower. This is why all work with data is done after preloading it in RAM. Thus, main memory is being used as a cache for data from the external storage. Anyway, a hard drive also has a cache on its own. On CPU Crystal, there are several levels of data caches, usually 3, L1, L2, L3. Their size is much smaller than the size of main memory, but they are much faster too. The closest level to the CPU is almost as close as registers. That's interesting. Additionally, CPUs possess at least an instruction cache, queue storing instructions, and a translation look-aside buffer to improve virtual memory performance. Registers are even faster than caches and smaller, so they are a cache on their own. Why is this situation so pervasive? An information system which does not need to give strict guarantees about its performance levels introducing caches often decreases the average access time, the time between a request and a response. To make it work, we need our old friendly locality. In each moment of time, we only have a small working set of data. The virtual memory mechanism allows us, among other things, to use physical memory as a cache for chunks of program code and data. Cool. Forward to motivation. Naturally, given a single task system where there's only one program running at any moment of time, it is wise just to put it directly into physical memory, starting at some fixed address. Other components, device drivers, libraries, can also be placed into memory in some fixed order. In a multitasking-friendly system, however, we prefer a framework supporting a parallel or pseudo-parallel execution of multiple programs. In this case, an operating system needs some kind of memory management to deal with these challenges. Executing programs of arbitrary size may be even greater than physical memory size. Oh, these are the challenges, okay. Executing programs of arbitrary size may be even greater than physical memory size. It depends on ability to load only those parts of program we need in the near future. Having several programs in memory at the same time, programs can interact with external devices whose response time is usually slow. During a request to a slow piece of hardware that may last thousands of cycles, we want to lend precious CPUs to other programs. Fast switching between programs is only possible if they are already in memory. Otherwise, we have to spend much time retrieving them from external storage. Storing programs in any place of physical memory. If we achieve that, we can load pieces of programs in any free part of the memory, even if they're using absolute addressing. In the case of absolute addressing, move rx this, all addresses including starting addresses become fixed. All exact address values are written in machine code. Freeing programs from memory management tasks as much as possible. While I've had the sneezes recently. While programming, we do not want to think about how different memory chips on our target and architectures can function. What is the amount of physical memory available, etc. Programmers should pay closer attention to program logic instead. Effective usage of shared data and code. Whenever several programs want to access the same data or code, libraries, files, it is a waste to duplicate the memory for each additional user. Yep. Virtual memory usage addresses these challenges. Address space. Address space is a range of addresses. We see two types of address spaces. One, physical address, which is used to access the byte on the real hardware. Naturally, there's a certain memory capacity a processor cannot exceed. It is based on addressing capabilities. For example, a 32-bit system cannot address more than 4 gigs of memory per process, because 2 to the 32 different addresses roughly correspond to 4 gigabytes of address memory. However, we could put less memory inside the machine capable of addressing 4 gigs, like 1 gig or 2 gig. In this case, some addresses of a physical address space will become forbidden because there's no real memory cells behind them. Logical address is the address as an application sees it. In instruction move rex this, there is a logical address this. A programmer has an illusion that he is the sole memory user. Whatever memory cell he addresses, he never sees data or instructions of other programmers, which are running with his own parallel. Physical memory holds several programs at a time, however. In our circumstances, virtual address is synonymous to logical address. Okay. Translation between these two address types is formed by a hardware entity called Memory Management Unit, MMU, with help of multiple translation tables residing in memory. Features. Virtual memory is an abstraction over physical memory. Without it, we would work directly with physical memory addresses. In the presence of virtual memory, we can pretend that every program is the only memory consumer because it is isolated from others in its own address space. The address space of a single process is split into pages of equal length, usually 4 kilobytes. These pages are then dynamically managed. Some of them can be backed up to external storage in a swap file and brought back in case of need. Virtual memory offers some useful features by assigning an unusual meaning to memory operations, read-write on certain memory pages. We can communicate with external devices by means of memory mapped input-output. By writing to the addresses assigned to some device and reading from them. Some pages can correspond to files taken from external storage with the help of the operating system and file system. Some pages can be shared among several processes. Most addresses are forbidden, their values not defined, and an attempt to access them results in an error. An interrupt page fault will occur. This situation usually results in abnormal termination of program. Linux and other Unix-based systems use a signal mechanism to notify applications of exceptional situations. It is possible to assign a handler to almost all types of signals. Accessing a forbidden address will be intercepted by the operating system, which will throw a SIG SEGV signal at the application. It's quite common to see an error message, segmentation fault, in this situation. Some pages correspond to files taken from storage, executable file itself, libraries, etc., but some do not. These anonymous pages correspond to memory regions of stack and heap, dynamically allocated memory. They are called so because there are no names in file system to which they correspond. To the contrary, an image of the running executable data files and devices, which are abstracted as files too, all have names in the file system. A continuous area of memory is called a region if it starts at an address which is a multiple of a page size. Example, or like 4 kilobytes, yeah. All its pages have the same permissions, okay. If the free physical memory is over, some pages can be swapped to external storage and stored in a swap file, or just discarded in case they correspond to some files in file system and were not changed, for example. In Windows, the file is called pagefile.sys. In StarNext systems, a dedicated partition is usually located on disk. The choice of pages to be swapped is described by one of the replacement strategies, such as least recently used, random. Any kind of system with caching has a replacement strategy. I'm not going to do that quite yet. Each each process has a working set of pages. It consists of his exclusive pages present in physical memory. Allocation. What happens when a process needs more memory? It cannot get more pages on its own, so it asks the operating system for more pages. The system provides it with additional addresses. Dynamic memory allocation in higher level languages, C++, Java, C#, etc., eventually ends up querying pages from the operating system using the allocated pages until the process runs out of memory and then querying more pages. Example, accessing a forbidden address. Now we are going to see a memory map of a single process with our own eyes. It shows which pages are available and what they correspond to. We'll observe different kinds of memory regions, corresponding to executable file loaded in memory itself, corresponding to code libraries, corresponding to stack and heap, which are anonymous pages, just empty regions of forbidden addresses. Linux offers us an easy-to-use mechanism to explore various useful information about processes, called procfs. It implements a special purpose file system, where by navigating directories and viewing files, one can get access to any process's memory, environment variables, etc. The file system is mounted in the proc directory. Most notably, the file procpid map shows a memory map of processes with identifier PID. Whoa, here we are. There's no PID. Oh wait, maybe these are the PIDs. Like 35. Yeah, I know PID stands for process ID. I just wasn't sure whether this meant like there's actually a directory called PID or whether this is just like a standing in for another process ID. I'm guessing it's just standing in. Interesting. Thank you, Mr. Nibbles. Okay. Let's write a simple program which enters a loop and thus does not terminate. It will allow us to see its memory layout while it's running. Let's try it. Stands for the actual PID number. Cool. Scratchpad. Mappings loop. Section data, correct, Dairy Queen, -1. Section text. What is this? Oh, just to make it all ones, I guess. Global start. And here's start. We're just going to jump to start. Okay. And then we'll try what he does here. So compile it. What do I call it? Oh, he's calling the output main.o. And then (4884). Sure enough, there's something. Looks like I don't have quite enough room to... There we go. That's interesting. Left column defines the memory range. As you may notice, all regions are contained between addresses ending with 3 hexadecimal zeros. The reason is that they are composed of pages whose size is 4 kilobytes each, which is 1,000, or OX 1000 bytes. Excuse me. We observe that different sections defined in the assembly file are loaded as different regions. The first region corresponds to the code section and holds encoded instructions. The second corresponds to data. As you see, the address space is huge and spans from the 0th to the 64 minus 1th byte. However, only a few addresses are allocated. The rest are being forbidden. The second column shows read, write, and execution permissions on pages, which is these, right? Looks like the Shema things, right? It also indicates whether the page is shared among several processes or is private to the specific process. And then it's asking me to read about that and that. This and this. Trying to get me to make a calendar event. I'll skip over that for now. So far we did nothing wrong. Let's try to write into a forbidden location. Producing segfault. Segfault bad adder. Or bad address, I guess. Sure, let's try it. Or we're already in NVIM, no? Oh, you guys want me to cast my keystrokes? There we go. Okay. There we go. Section data. That's what he's doing. And then cool. And then if I run that, it'll sure enough, it's segfaults. We're accessing forbidden memory at this address, which is 1 byte before the code segment starts. This address is forbidden, and hence the writing attempt results in a segmentation fault, as the message suggests. Efficiency. Loading a missing page into physical memory from a swap file is a very costly operation, involving a huge amount of work from the operating system. How come this mechanism turned out not only to be effective memory-wise, but also to perform adequately? The key success factors are: 1. Thanks to locality, the need to load additional pages occurs rarely. In the worst case, we have indeed a very slow access. However, such cases are extremely rare. Average access time stays low. In other words, we rarely try to access a page which is not loaded in physical memory. It is clear that efficiency could not be achieved without the help of special hardware. Without a cache of translated page addresses, TLB, translation look-aside buffer, we would have to use a translation mechanism all the time. TLB stores a starting physical address for some page we will be likely to work with. If we translate a virtual address inside one of these pages, the page start will be immediately fetched from TLB. In other words, we rarely try to translate an address from a page that we did not recently locate in physical memory. Remember that a program that uses less memory can be faster because it provides fewer page faults. Okay, implementation. Now we're going to dive into details of how exactly the translation happens. Interesting. For now, we only talk about a dominant case of 4 kilobyte pages. Page size can be tuned, and other parameters will change accordingly. Refer to section 473 for additional details. Virtual address structure. Each virtual 64-bit address, like ones we are using in our programs, consists of several fields as shown in figure 4.1. 63 through 48 is the sign extension. 47 through 38 is the index and level 4 page map table. 38 through 30 is index and page directory pointer table. 29 through 21 is index and page directory. 20 through 12 is index and page table. And 11 through 0 is offset from page start. Okay. The address itself is in fact only 48 bits wide. It is sign extended to a 64-bit canonical address. Its characteristic is that its 17 left bits are equal. If the condition is not satisfied, the address gets rejected immediately when used. Then 48 bits of virtual address are transformed into 52 bits of physical address with the help of special tables. Bus error. When occasionally using a non-canonical address, you will see another error message. Bus error. Oh, that's what a bus error means? Physical address space is divided into slots to be filled with virtual pages. These slots are called page frames. There are no gaps between them, so they always start from an address ending with 12 0 bits. The least significant 12 bits of virtual address in a physical page correspond to the address offset inside page, so they're equal. The other 4 parts of virtual address represent indexes in translation tables. Each table occupies exactly 4 kilobytes to fill an entire memory page. Each record is 64 bits wide. It stores a part of the next table starting address as well as some service flags. Address translation in depth. Figure 4.2 reflects the address translation process. Oh, dearie me. Here we go. We got a thumbnail for this video. This is a mess. First, we take the first table starting address from CR3. This guy. The table is called page map level 4, PML4. Fetching elements from PML4 is performed as follows. Bits 51 to 12 are okay, this is like a bunch of implementation details that I'll probably get to when I write my own paging system. The process iterates through 2 more tables until at least we fetch the page frame address. To be precise, it's those bits. Are we going to perform so many memory reads instead of 1 now? Yes, it does look bulky. However, thanks to the page address cache, TLB, we usually access memory on already translated and memorized pages. We should only add the correct offset inside page, which is blazingly fast. As TLB is an associative cache, it is quickly providing us with translated page addresses, giving a started virtual address of the page. Note that translation pages can be cached for faster access. Figure 4.3 specifies the page table entry format. Deleted users gotta go. Cast is gonna start. See you on Lonely live stream. I haven't yet decided whether I'm gonna do a Lonely one today, but I'll see ya at some point anyway, right? Alright, and then that thing, and this is a table for it. If P is not set, an attempt to access the page results in an interrupt code. Page fault. The operating system can handle it and load the respective page. It can also be used to implement lazy file memory mappings. The file parts will be loaded in memory as needed. The operating system uses dub-bit to protect the page from being modified. Okay. In general, segmentation faults occur when there's an attempt to access memory with insufficient permissions, like writing into read-only memory. In case of forbidden addresses, we can consider them to have no valid permissions, so accessing them is just a particular case of memory access with insufficient permissions. EXP, also called NX, forbids code execution. That bit forbids code execution. The DEP, data execution prevention technology, is based on it. When a program is being executed, parts of its input can be stored in a stack or its data section. A malicious user can exploit its vulnerabilities to mix encoded instructions into the input and then execute them. However, if the data stack and stack section pages are marked with EXP, no instructions can be executed from them. The .text section, however, will remain executable, but it is usually protected from any modifications by a dub bit anyway. Cool. Page sizes. The structure of tables of different hierarchy levels is very much alike. Okay. Sorry, I'm going kind of fast. I'm trying to move through this a little bit quicker than I have been. Memory mapping. Mapping means projection, making correspondence between entities. Yep. File, devices, physical memory. In virtual memory regions, when a loader fills the process's address space, when a process requests pages from the operating system, when the operating system projects files from a disk on a process's address spaces, these are examples of memory mapping. A system called mmap is used for all types of memory mapping. To perform it, we follow the same simple steps described in Chapter 2. Table 4.1 shows its arguments. So it's a system call, mmap. 0 is the identifier. Or sorry, not 0, 9. RDI. Operating system. Okay, RDI holds adder, which an operating system attempts to map into pages starting from this specific address. This address should correspond to a page start. A 0 address indicates that the operating system is free to choose any start. Don't know if this was mentioned before from Mr. Nibbles, but a fault during a fault handler is allowed to happen called a double fault, which can be used to load a missing page in memory, but a triple fault will cause a CPU reset. Interesting. No, I had no idea. That's interesting. This will be the region size and RSI, RDX, protection flags, R10, utility flags, shared or private, anonymous pages, etc. Okay. R8, optional descriptor of a mapped file. The file should therefore be opened. R9 is the offset in file. After call to mmap, REX will, excuse me, had to sneeze there again. RX will hold a pointer to newly allocated pages. Example, a mapping file into memory. We need another system call, namely open. It is used to open a file by name and to acquire its descriptor. See table 4.2 for its details. So cool. 2 is open. This gets the file name, which is a pointer to a null terminated string. Name.holding file. Flags, a combination of permission flags, read only, write only, or both. And the mode, if this open is called to create a file, it will hold its file system permissions. Mapping file in memory is done in 3 simple steps. Open a file using open system call. REX will hold file descriptor. Call mmap with relevant arguments. One of them will be the file descriptor acquired at step 1. Use print string routine we have created in chapter 2. For the sake of brevity, we omit file closing and error checks. Okay. Mnemonic names for constants. Linux was written in C, so to ease interaction with it, some useful constants are predefined in a C way. The line define name 42 defines substitution performed in compile time. Whenever a programmer writes a name, the compiler substitutes it with 42. Yep. This is useful to create mnemonic names for various constants. NASM provides similar functionality using these Oh yeah, this is what Stefan was showing me, right? It literally looks almost identical. See section 5.1 preprocessor for more details on how such substitutions are made. Let's take a look at a man page for mmap system call describing its third argument, prot. The prot argument describes the desired memory protection of the mapping. It must not conflict with the open mode of the file. It is either prot none or the bitwise or none of the following, or more of the following flags. Those, which is prot exact, prot read, prot write, and prot none. Prot none and its friends are examples of such mnemonic names for integers used to control mmap behavior. Remember that both C and NASM allow you to perform compile time computations on constant values, including bitwise and or operations. Following is an example of such computation. Cool. Unless you're writing in C or C++, you will have to check these predefined values somewhere and copy them to your program. Following is how to know the specific values of these constants for Linux. 1. Search them in header files of the Linux API and user include. Use one of the Linux... Okay, this is for Linux stuff. We do recommend the second way for now, as we do not know C yet, but shortly we will. You may even use a search engine like Google and type that. Okay, sure. Dabba. Okay, complete example. Let's do it. Complete example. Create a file test.txt. With any contents. Like what? There we go. How's that? And then launch the file listed in listing 4.4 in the same directory. You'll see contents written as standard out. Let's try it. So there's test. Let's make another one called mmap.asm. We're gonna say define. Oh, oop dear. O, where's O? There we go. O, read only, I'm guessing, 0. No. Protection read, OX1. Define map private. Copilot, you're really bothering me. Okay, map private is OX2, and then you say section data fname db test.txt 0. Null terminated, right? So we have the 0 here. It's the file name, okay. Then we have the section .text global start. Then we make like a print string, which we've done this before. Push RDI. Pop RSI. Oops. Okay. So this is open. And then here we have mmap. Cool, let's see if this thing works. Check it out. That's really cool, totally printed it out. That's neat. I'm going to raise my desk a smidge. Okay. Summary. In this chapter, we got a bunch of questions. All right, in this chapter, we have studied the concept and the implementation of virtual memory. We have elaborated it as a particular case of caching. Then we have reviewed the different types of address spaces, physical or virtual, and the connection between them through a setup to translation tables. Then we dived into the virtual memory implementation details. Finally, we have provided a minimal working example of the memory the mapping using Linux system calls. We will use it again in the assignment for chapter 13, where we will base our dynamic memory allocator on it. In the next chapter, we are going to study the process of translation and linkage to see how an operating system uses the virtual memory mechanism to load and execute programs. Question 50. What is a virtual memory region? I gave all the requirements up here, right? Like it has to start at a 4 kilobyte offset. Like I said, it's called a region if I forget where it was. But it's like a continuous section of memory that starts at a 4 kilobyte offset, I think. What will happen if you try to modify the program execution during its execution? The execution code during its execution? Probably a seg fault. What are forbidden addresses? They're addresses that don't give you permissions to do anything to them. What is a canonical address? Ooh, I forget. We'll skip that one for now. What are translation tables? Mapping a file to memory like that is often used to make parsers faster. Using system calls to perform reads from file descriptors is a bit slower. Okay. Thank you, Mr. Nibbles. Mr. Nibbles, are you on the Discord? All right, what is a what was that? Page frame? Frame. I remember what a page is, but what's a page frame? Is that the same thing, maybe? No, yeah, also I didn't get a chance to finish your last video on writing a parser. Yeah, no worries. There's sort of like two projects going on in tandem. This is the operating system one, which is just me learning assembly for now. And the other one's the language thing, which I ultimately want to write the operating system in. Language on hold. No, the language isn't on hold. This is just, I'm doing kind of two things at once here. So this is the other thing. A memory region. Oh, that's what I answered for this. Well, this one is just like the virtual one, right? Where like that ends up mapping onto physical memory, but like when you're working inside of it, you have no idea. Unless you try to go outside of it and then you get psych faulted. What is the virtual address space? How is it different from the physical one? What is the translation look aside buffer? That's all up there. Most of these I can just refer to if I need them later, right? So I don't feel the need to like fully understand all of this. Because eventually I need to make a paging system, right? And then I'll have to really dig into this a little more. So, how is the address space switched? Most kernels avoid faulting in kernel memory. That's a good way to get a nasty deadlock. Gotcha. How is the address space switched? Which protection mechanisms does virtual memory incorporate? What is the purpose of EXP bit? That was the one that like said you can't execute or you can't modify it or something. I forget. What is the structure of the virtual address? Does a virtual and physical address have anything in common? If we write a string in .text section, what happens if we read it? And if we overwrite it, write a program that will call stat open mmap system calls. I'm not going to do these right now. Write the following programs which all map a text file input.txt containing an integer x in memory using an mmap system call and output the following. Factorial. These would be fun. But for the sake of moving along, I think I'm going to pass over them for now. Cool. I was thinking I'll go today till sometime between 7 and 7:30, so I'll keep going for now. I'll start chapter 5. Compilation pipeline. This chapter covers the compilation process. We divide it into 3 main stages: preprocessing, translation, and linking. 5.1 shows an exemplary compilation process. There are 2 source files, first.asm and second.asm, each treated separately before linking stage. It goes in the preprocessor and then the compiler, makes second.o. Oh, code substitutions. This is probably where you replace those like, what do you call them? They're kind of like macros, but they're like not. Like these things, right? I'm guessing this step is where those get replaced, right? Code substitutions. Then you compile, you get these object files, and then you link them together in the linker, and you get an executable, and then the loader. Oh, and libraries get pulled in with the linker too. Interesting. Preprocessor transforms a program source to obtain another program in the same language. The transformations are usually substitutions of one string instead of others. Compiler transforms each source file into a file with encoded machine instructions. However, such a file is not yet ready to be executed because it lacks the right connections with the other separately compiled files. We are talking about cases in which instructions address data instructions, which are declared in other files. Yeah, and see any line starting with the octothorpe is a preprocessor statement. Gotcha. Okay, I do kind of remember that. Linker establishes connections between files and makes an executable file. After that, the program is ready to be run. Linkers operate with object files whose typical formats are ELF, executable and linkable format, and this common object file format. Loader accepts an executable file. Such files usually have a structured view with metadata included. It then fills the fresh address space of a newborn process with its instructions, stack, globally defined data, and runtime code provided by the operating system. The preprocessor. Each program is created as a text. The first stage of compilation is called preprocessing. During this stage, a special program is evaluating preprocessor directives found in the program source. According to them, textual substitutions are made. As a result, we get a modified source code without preprocessor directives written in the same programming language. In this section, we are going to discuss the usage of the NASM macroprocessor. Oh, so they are called macros. Simple substitutions. One of the basic preprocessor directives is called define, %define. It performs a simple substitution. Given the code shown in listing 5.1, a preprocessor will substitute cat count by 42 whenever it encounters such a substring in the program source. Okay. To see the preprocessing results for an input file.asm, run this. Ooh, I want to try that. Cat count.asm. I'm gonna say define cat count to be 42. Then here I move and then here I'm going to say how do you do it? Oh yeah, NASM dash big E cat count. Sure enough, I substituted 42 in for cat count. That's really interesting. Commands to declare substitutions are called macros. During a process called macro expansion, their occurrences are replaced with pieces of text. The resulting text fragments are called macro instances. In listing 5.2, a number 42 in line move rax cat count is a macro instance. Names such as cat count are often referred to as preprocessor symbols. NASM allows you to redefine existing preprocessor symbols. How do you guys feel about macros generally in languages? Like I'm thinking like Swift and Rust macros. Do you think Lonely should have macros? Or something more like Zig comp time? Or something totally different? Or nothing like that at all? I'm curious. It is important that the processor knows little to nothing about the programming language syntax. The latter defines valid language constructions. For example, the code shown in listing 5.3 is correct. It doesn't matter if neither A or B, nor B alone, constitutes a valid assembly instruction. As long as the final result of substitutions is syntactically valid, the compiler is fine with it. Depends. Implement macros when you need them. You can get far with just constant definitions. Yeah, for sure I wouldn't implement macros anytime soon. Yeah. Zig comp time is cool. Zig comp time is very cool. Oops. I feel like the Zig language server isn't quite right now what it could be. I feel like it could be like amazing because of how comp time works, you know. But there's things about macros that just are like sometimes they're just too magical, and that kind of annoys me. But then sometimes they're like beautiful, and then I'm like, whoa. Like in Rust, have you guys used SQLX? I have this like SQLX or that one like .env crate, like those two crates in Rust where you get like you literally get compile time type errors if you're like referencing the wrong table. It's just like a raw string. You get to write like raw SQL queries, but I don't know, it's pretty amazing. Or like type checked .env files, like if you, yeah, it's amazing. Where was that? Okay, for example, the code shown in listing 5.3 is correct. It doesn't matter if neither B nor A nor B alone constitutes a valid assembly instruction. As long as the final result is of substitutions and is syntactically valid, the compiler is fine with it. Oh, so it's like C where you can just like literally write anything in here. So A becomes move RAX, and this becomes RBX. So it becomes move RAX, RBX. Another example, in higher level languages, an if statement has a form of if expression, then statement, else statement. Macros can operate parts of this construction which on their own are not syntactically correct. Like just an else, okay. As long as the result is syntactically correct, the compiler will have no problems with it. Interesting. Contrarily, other types of macros exist, namely syntactic macros tied to the language structure and operating with its constructions. Such macros modify them in a structured way. Languages like Lisp, OCaml, and Scala use syntactic macros. Yeah, I would. If I made macros, I think I'd make syntactic macros, not just text-based. Why are we using macros at all? Apart from automation, which we will see later, they provide mnemonics for pieces of code. For constants, it allows us to distinguish occurrences of 42, which are used to count cats, from those used to count dogs or whatever else. It's a good example. Otherwise, certain program modifications would be more painful and error-prone, since we would have had to make more decisions based on what the specific number means. For packs of language constructs, it provides us with a certain automatization, just as subroutines do. Macros are expanded at compiled time, while routines are executed in runtime. The choice is up to you. For assembly, no optimizations are performed on programs. However, in higher level languages, people use global constant variables for that matter. A good compiler will substitute its occurrences with its value. A bad one, however, cannot be aware of optimizations, which can be the case when programming microcontrollers or applications for exotic operating systems. In such cases, people often do a compiler's job by using macros as an assembly language. It is a good practice to name all constants in your program. Okay. In assembly and C, people usually define global constants using macro definitions. Substitutions with arguments. Macros are better than that. They can have arguments. Whoa. Who knew? Listing 5.4 shows a simple macro with 3 arguments. Whoa. That's interesting. Its action. Its action is simple. For each argument, it will create a quad word data entry. As you see, arguments are referred to by their indices starting at 1. When the macro is defined, a line test 666, 555, and 444 will be replaced by those shown in listing 5.5. That's really interesting. Simple conditional substitution. Macros and NASM support various conditionals. The simplest of them is %if. Listing 5.6 shows a minimal example. If x double equals 10. Well, this is just like... Oh, but you can only check this against like macros. Mr. Nibbles. Oh my word. That's so bad. New programmer walks into a bar. 2 macros were arguing. The programmer says, "Whoa, I didn't know macros could have arguments." Man. This is interesting, for sure. Ooh, elif, that's else if, I'm guessing. And else. And then you end if. Cool. This shows an instantiated macro. Remember, you can check the pre-processing result using NASM-E. Wait, what? %line? I don't get this. The condition is an expression similar to what you might see in high-level languages, arithmetics, and logical conjectures, and or not. Conditioning on definition. It is possible to decide in compile time whether a part of file should be assembled or not. One of many %if counterparts is if-def. It works in a similar way, but the condition is satisfied if a certain preprocessor symbol is defined. An example shown in listing 5.8 incorporates such a directive. If def flag, then we do hello string. That's interesting. As you can see, the symbol flag is not used here. Is not defined here using the %define directive. Thus, we have the line labeled by hello string. It is worth mentioning that preprocessor symbols can be defined directly when calling NASM thanks to the -D key. For example, macro condition in listening 5.8 will be satisfied when NASM is called with -D myFlag argument. Check the preprocessor output on file shown in listening 5.8. Okay. In the next sections, we are going to see more preprocessor directives similar to %f. Conditioning. Oh, it is 7 o'clock, isn't it? This is a pretty long chapter, isn't it? This is quite a long chapter. Wow. Okay, and then inputs and interrupts and system calls. And then after interrupts and system calls, there's models computation. So there's the one we're in, and then there's interrupts and system calls, and then there's this one, which is long. And then there's C. Okay, so this is the chapter we're in, then there's 2 more, and then we're going to be writing C. Good grief, you slept 18 hours? That's amazing. I've definitely never done that in my life. All right, I'm going to stop where if I can find where we were. Where was I? Right here. Conditioning untext identity. I'll highlight this so we remember. And yeah, pick back up tomorrow. I think I'm going to do another one of these tomorrow morning. Roughly the same time, 6 or 6:30 EST. And yeah, thanks all for joining and for the help. Until next time. Oh, I might do a lonely stream later today. Not sure yet. I'll ping the Discord and schedule it on YouTube. So cool. Thanks everybody. Until next time.